my talk about serialization and object graph communication. My name is Florian Habermann, and I'm with MicroStream. And we will talk about how to get objects into binary state and back, send it over the wire, and so on, and what it's all about, the fuss with the serialization. The mandatory safe harbor, of course. So what is serialization? How does it work? Simply said, it is a conversion from Java objects to binary state and back. That's all about serialization there. So the graphs are converted in a transportable format, for example, a byte stream or human readable formats like XML or JSON, and then they are converted back on the receiver side. So you can transfer the data over the network or store data in caches, or just transfer them from one JVM to another, or to achieve a persistent state of your objects and restore the instances later on. Yeah, it's used basically everywhere in the Java world. So we use it for stream processing, data grids, the remote method invocation uses it heavily. A lot of web frameworks use it to store user sessions, for example, or application servers. Of course, web and REST services, which convert Java objects to JSON, for example, as a payload to transfer the data to the caller. Caches use it heavily if you use store by value, not store by reference. Store by value meaning the binary state of object is stored and not just the reference, and then you get an object copy back if you make a cache get later on. Key value stores and search indices use it as well, like Lucene and Apache Solr. So as you can see, the serialization is everywhere in the Java world, and there have been a lot of talks about its shortcomings, about its flaws, and what is that all about? Like, Mark Reynolds said it was a horrible mistake. And yeah, he's probably right, because most of the vulnerabilities in Java can be linked to the current Java serialization. And Brian gets even more drastic. He says it makes every mistake imaginable and imposes an ongoing tax, of course, because it can't be changed in a way that it stays backward compatible, and to eliminate all flaws. So basically we have to keep up with it, and like we see in this vulnerabilities report, if you go into the CVE database and just search for Javalization, you get thousands of vulnerabilities throughout the Java ecosystem. A lot of frameworks which use the serialization inherit these bugs or have bugs based on this. A lot of critical stuff gets fixed, of course, but this is an ongoing problem. One of the biggest or most heard of is basically the struts vulnerability, maybe. There were thousands of affected servers which had to close the gap as fast as they can, because there were published attacks and how to attack a server which contains the strut web framework. And in the JDK itself, well over a few hundred issues open regarding the serialization. So the biggest vulnerabilities, of course, all the serializable classes which are in a class path of your application can be serialized or deserialized automatically. And creating and injecting malicious code is very scarily easy. So few more presenters as well at the JCON will show how easy it can be done, and to leverage the vulnerabilities to attack systems. So in later versions of the JDK, they introduced black and white listings that give a bit more security, of course. But you have to worry about it. You have to know what classes are used in your application, what classes get serialized and deserialized, and provide a proper listing by yourself. And since it's basically used everywhere, you have to scan your whole libraries and create a library of classes. So that's probably not a feasible approach, because most of your dependencies will use Java serialization at some point in time. Yeah. And of course, the built-in Java serialization in a JDK has some limitations. All classes which you will use must implement the Java IO serializable interface. And it doesn't have really an API contract, but uses magic methods you have to implement in your classes to customize this the serialization, deserialization functionality. And objects from third-party APIs which don't implement the serializable interface can't be serialized. Full stop. So you can't bring serialization functionality back into third-party libraries which you want to use, for example. And after the deserialization, you always get an object copy, so you can't update your object graphs partially. So only snapshotting can be done, and therefore the keeping your object graph synchronous automatically is not possible with the current serialization libraries. Alternatives to the JDK serialization are external libraries. Most of them, a lot of them are bytecode based, but they make them the same conceptual mistakes as well. And another problem is the depth of the object graph is limited by the stack size, because the framework uses stack-based recursion, meaning if you have a deeper going object graph, you will run into stack overflow errors. And that's one limitation. Other frameworks use human readable formats like XML and JSON, and the format itself has shortcomings, like JSON, for example. It's just a tree structure, so you can't have cyclic references. Multiple referenced objects are just written multiple times in your JSON document, so it gets bloated very quickly. Of course, it's focused on human readability. That's a good point of this format, but it's a needless overhead for machines. You have an overhead of by parsing this format. It's a loss of performance, and it's not really suited for bigger amounts of data and complex object graphs. Like I said, the circular references cannot be handled because the formats don't have the capabilities for it. So there is a proposal by Brian Goetz towards better serialization. You can look it up. It's a longer document. He describes all the status quo, what mistakes were made, and what they want to do to make serialization better and more secure. But the concept has flaws as well in my eyes. They will still break the referential integrity when deserializing the object graph. It still violates the separation of concerns because you have to put your customization logic into your object graphs, and it's only on draft for an API and not an implementation. So the JDK will only provide a standard API-based, interface-based, I guess, and they are dependent on third-party implementations which are still to come. So we will see where the road is going. But back when we had the idea for the microstream storage engine, we scanned the serialization libraries and we saw, yeah, we cannot really use an existing one for our purposes because of the flaws and shortcomings. So we had to come up with a completely new Java serialization. And that's the base of all microstream libraries, most used, of course, in our storage engine. And this serialization is developed newly from ground up. It is designed to eliminate the shortcomings of existing serialization frameworks and is optimized for security, flexibility, and performance. And it's used in all microstream modules heavily in our persistence or storage and our object graph communication library. So what's the difference or what do we do differently to existing serializing frameworks? So we separate data and metadata. So the information of the structure of the transferred types called metadata is separated from the raw data in a data stream. So the Java serializer transfers the class information within the stream where the raw data is transferred, and this makes manipulation very easy and has different drawbacks. So we decided to separate the data from the metadata. We do not execute code at the deserialization process, which makes injecting malicious code impossible. So this eliminates a big security flaw. And the referential integrity is secured because we using Swizzling inside, which is an a object reference mapping. Every object gets assigned an ID internally by the engine, and because of that we can minimize the data load and ensure the referential integrity of the deserialization at any time. And because of that, we are also possible or able to store and restore object graphs partially and keep the referential integrity. So we can transfer partial object graphs and merge it into existing ones. And one feature of this is, of course, the persistence engine. Or you can keep object graphs synchronous over various machines. So how does it work? When microstream serializer first sees classes, he will analyze them and create metadata. It's a one-time process because the metadata is cached. It analyzes the current runtime versions of all required entity and value type classes and derives an optimized metadata from them. So the same is done when encountering a class at runtime that was unknown so far. The analysis is done by reflection, but since it is only done once for every handled class, the reflection performance cost is negligible. And the actual storing and loading of serialization and deserialization is done via an optimized framework code based on this created metadata. And if the class layout changes, the type analysis creates a mapping from the field layout that the class's instances are stored into that of the current class of the runtime. It's possibly automatically, unambiguous changes or via some configurable heuristics, otherwise by a user-provided mapping. So you can evolve your classes in the runtime through the lifecycle of your application and still keep your data. We call it legacy type mapping. and therefore you can evolve your types as many times as you like, and keep and map your data to the made changes. So the performance stays the same here, even with legacy type mapping, because we only map the change the data to the change types at on demand, and the JVM does simply not care if you copy a loaded value to position 3 or position 5 in the memory. If you move the field, for example, it's all described in the metadata, so you don't have to worry about performance loss if you change your classes. It is done on demand, like I said. Not the whole storage or data block is written, rewritten if you change your classes, but the bytecode gets transferred to your class layout on demand if you deserialize the values. So at deserialization, the incoming data is put off heap, and then the objects are created in memory. In the second phase, they are populated, so meaning the values are the primitive values are written to the objects, and then the linking phase is the last one, meaning the references get put together again, restoring the referential integrity. So, and we don't use stack-based recursive linking. We don't use stack-based, but recursive linking. And that supports an arbitrary depth of object graphs. So you don't have to worry to run into Stack Overflow problems here. And on the other hand, we don't generate any code. We don't do any bytecode hacking, replacement of instances by proxy types or similar monkey business. And you don't have to implement serializable or any other interface. Don't have to extend from any class. Don't use annotations. Just define your poachers as they are, and MicroStream can serialize and deserialize it. And if you have to customize the serialization process, we will use external type handlers for that, which I will show you later on. So it has no limitations. Any object can be serialized. Like I said, no special implementation stuff. The external handlers and the external ones have another good thing is that you can use objects from third-party APIs, basically any object which is in a class path, and the depth of the graph is not limited, and you can cover the class changes through our legacy type mapping at the application's lifecycle. And with the optimized format, byte format, we can achieve, of course, a good performance values. So redundancy-free data transfer, because multiple referenced objects are written only once and referenced by their ID. We don't have needless overhead by string formats like JSON or XML. And we had done a test with about 100,000 Java objects, and MicroStream Serializer does it in 59 milliseconds compared to existing ones. So performance is a big thing as well. Yeah. So it's easy to use. It's pure Java, and you don't have further external dependencies except MicroStream. No internal configuration is needed. You can use your classes as they are, or use third-party classes as they are. And so therefore any object can be serialized, and it fits seamlessly, of course, to the Java object model. Ensures a high secure data transfer, redundancy-free, and it's just a simple Java library available in Maven Central. And it's part of the big MicroStream library where the storage engine lies in as well. So if you want to customize the serialization or deserialization process, you can use custom type handlers. A type handler basically is a class which is responsible how a single Java type is put into a binary format and back. And you can take control over the storing and loading procedure. You can optimize, of course, the memory footprint and the performance. And it is an external configuration for any type. You don't put your serialization customization into your purchase like you do with the Java serialization, but you define external types, handlers, and you can customize third-party libraries with this as well. Multi-stream comes with a lot of predefined, optimized type handlers for the most commonly used types like the collections in a JDK or local date and local time types, and many more. And for every other type, generic type handlers being generated by the engine at runtime, which use the metadata generator to analyze the types and then store the types accordingly. But if you want to optimize performance and memory footprint, you can, of course, implement a custom type handler. Let's look at an example here. We have a time slot type with a slot number and a start and end date. And for MicroStream's generic type handler, this will be 3 records because every object instance will be stored as a single record. We have the time slot itself, a primitive value, and 2 date instances. So meaning this time slot gets written as 3 records in a storage. The time slot itself, it's split up into primitive data, which is the slot number, and then we have the 2 date instances with their timestamps, and the object's ID is then referenced in a time slot, which is done by the Swissling internally. Now that's a lot of data for a simple time slot data type, and if you have a lot of instances, for example, you have machines which read millions or billions of records in your database, then you want to optimize the memory footprint and the performance, and it could look like that. Instead of using references and write the data as new records, just put the timestamps of the dates inside the time slot record, and you can get the memory footprint down by a third. And that's a good achievement for a simple customization. Can be done in several ways. You can use a builder API. You create a type handler for the time slot type, and then you define binary fields with the readers and the writers. Reading means the slot number gets written, and at deserialization, the slot number gets assigned again. You can do this for any field. You extract the timestamp at serialization and just create your new date object at the deserialization time. And that's all you have to do to create a custom type handler. In this case, just put a static method which returns a binary type handler into your type, which you want to customize, and MicroStream will use it automatically for that. You don't have to register anything, just put it there. So, but this would be an internal configuration. If you don't have access to the source code of certain types which you want to customize, you can use the external handlers as well. In this example, we want to customize the buffered image. It's a type in the JDK. Just extend from one of our predefined custom binary handlers. In this case, which create a custom value of type byte, meaning we decode the buffered image to a PNG file or to PNG bytes, and these bytes are stored in or serialized over the wire, and vice versa. We create a buffered image out of this PNG encoded stuff again. Afterwards, just register the type handler in the the foundation or the configuration layer of the serializer, and you're good to go. So what about class changes? For example, do you want to take control over the migration from the old version to another, and and for example, you want to split up a name to first and last name. This one requires customization, of course, because MicroStream doesn't know where to split the name. In this example, the most common cases, for example, primitive type conversions or simple field renames can be detected automatically, but structural changes must be customized. All right. Let's go back. So with this legacy type mapping, where the legacy type handlers get into play, ensures that the data will evolve with your class changes, and even over different JVMs and different or multiple changes of your classes can be handled, and therefore you can ensure that no data is lost or converted properly. So, and besides our storage engine, we have another module called Object Graph Communication, where the serialization engine is used. The object graphs can be serialized and update isolated through the deserialization, and it enables you to keep object graphs synchronously easily over various JVM instances. You can use the auto update to synchronize object graphs, or you can create copies of your object as well. If you want to use new instances for that, can be used in caches. Our cache implementation, which is compatible to JSR 107, uses the copy method for the store by value setting for caches. So the serializer always puts the binary data into the cache, and if you make a cache get, you get a new copy of the objects, which is the API contract of the Java Cache API, for example. So how to use our object graph communication is in a communication binary artifact. Just put it in your as a dependency using the management tool of your choice, in this example Maven, of course. And let's look at the end at a simple example. Just want to open a host. For that we use a foundation. It's a builder style configuration class. We bind our host to a certain address and port. You can use an optional whitelisting if you like, and then use the host channel acceptor to handle incoming data. In our example, we just send a customer. We call the receive method every time a request is made. This acceptor gets called, and we just send welcome customer name back and close the channel again. So, and that's all you have to do for a simple host of a serialization part or the communication part. And in the different JVM, we create a client, again with a foundation connected to the host's target address. Again, register entity types and create the client. So when the channel is connected, you just send a request to the server, send a new customer, and the server will reply with hello John Doe. So this is a simple example showing how to communicate between different JVMs to just a single customer here, but you can keep your graphs asynchronous with the COM layer here, And the new version of the COM layer also supports the legacy type handling. So you can use evolving classes over different JVMs. There are a lot of different integrations in the making or as prototypes available right now. This stuff I'm showing is, well, will be part of the version 8 release train coming up next year, besides our new distributed storage engine, which can span the object graph over multiple JVMs to scale horizontally. And therefore we'll use different parts of the technology or different modules which we will release as open source probably. One of them will be object graph streaming. So you can adopt JVMs to Kafka or Pulsar streaming frameworks to get a very easy and a quick serialization or object graph communication between different systems. And you can produce and consume all object graphs, of course. You have a type-safe streaming. You can use multiple source linking. You can use static and dynamic scoping of the types if you want to whitelist or to use every type. And we provide auto conversion for different external formats, so you can open up your objects to different languages as well. If you convert it to JSON, you can use the output with JavaScript, for example. Yeah. And it could look like that, for example, how you have a method which returns an object, returns an order, and takes an order and just validates it. It's just a simple example, and you can use the incoming order from a source, and the outgoing order is put in a target. So as source, you define a Kafka topic, and you put it to a Hazelcast node defined in some external library, external configuration file. And that's how you could do a multi-source linking, and the serialization engine will take care of the conversion of your order object in the background. So I'm running out of time here. And the integration is a big topic as well. Here at the MicroStream library, we have done Helidon, Spring Boot, and Micronaut right now. They are available in either our repository or at the Helidon release train. And these integrations make use of the serializer heavily as well. So we see it's becoming adopted around. So if you want to take a look at it, it's all open source. Check out our GitHub page, leave a like, and dig into the source code. We are always open for enhancement proposals or bug reports. And if you want to get started, just look at the examples at our GitHub, or of course at our documentation page. That's the best way to dive into this topic. So thanks for listening. Have fun at the other talks at the JCON. See you then.